there is a limit. Not a limit imposed by current technology, not a limit that better engines or smarter engineering will one day overcome. A fundamental limit, written into the structure of space-time itself, into the nature of space and time and how they expand. And that limit means the following. There is a portion of the universe, a vast, almost incomprehensibly large portion, that humanity will never reach. Not because the distances are too great and the journey too long, but because the space between us and those places is expanding faster than anything can move through it. They are already beyond reach, forever. Tonight, we are going to follow the physics of this limit honestly, precisely, all the way to its end. We will start with what we have achieved, move to what is in principle possible, and end with what is permanently, irreversibly, unreachably closed, not because of technological limitations, but because the universe is built this way. If you have this on because the night is long, stay. This is one of the strangest stories in physics. Not because it is exotic or speculative, but because it is real, and because its implications for our place in the universe are more significant than most people understand. Let us begin with the most immediate question. How far have we actually gone? The greatest distance any human has travelled from Earth is approximately 400,000 kilometres. During the Apollo missions between 1969 and 1972, the Moon, that was and remains the maximum human achievement in terms of distance. Since then, more than half a century, no human has gone farther than low Earth orbit. 400,000 kilometres. This sounds like a lot, but in the context of what we are discussing tonight, in the context of the actual scales of the solar system, the galaxy, and the universe, it is nothing. Literally nothing. The average distance from Earth to the Sun is approximately 150 million kilometres. We have travelled 400,000 of those. That is 0.27% of the distance to the Sun. Less than a third of 1% of the distance to the nearest star in our system. The distance to Mars, our next likely destination, varies from about 55 to 400 million kilometres, depending on orbital position. With current technology, the journey would take 7 to 9 months. This is achievable in principle. It is immensely difficult, but the physics allows it. The distance to Pluto, about 5.9 billion kilometres on average, with current speeds roughly 10 years one way. Also achievable in principle with a suitable spacecraft, though not yet for humans. The distance to the edge of the solar system, to the outer boundary of the Oort cloud, where the Sun's gravitational influence finally yields to other stars, is roughly 100,000 astronomical units, about 1.6 light-years. At current speeds, approximately 30,000 years. That is still the solar system. We have not yet reached even other stars. The nearest star, Proxima Centauri, is 4.24 light-years away. At the speed of Voyager 1, the fastest object we have ever launched, the journey would take approximately 73,000 years. The Milky Way is 100,000 light-years in diameter. The nearest large galaxy, Andromeda, is 2.537 million light-years away. The observable universe is approximately 93 billion light-years in diameter. These are numbers, large numbers, but they do not convey real meaning until we begin thinking about what it means to reach any of these places given the constraints physics imposes. Let us talk about the speed limit. In 1905, Einstein showed that the speed of light, approximately 299,792 kilometers per second, is the maximum speed at which any object with mass, any signal, any information can move. This is not an engineering constraint, it is a geometric property of space-time. As an object with mass approaches the speed of light, the energy required increases without bound. To reach exactly the speed of light would require infinite energy, so it does not happen. However, special relativity contains something potentially useful for interstellar travel: time dilation. Moving clocks run slow. This is not an illusion, it is a physical fact confirmed by countless experiments with atomic clocks on aircraft and satellites. For an object moving close to the speed of light, its own time passes significantly more slowly than for stationary observers. This means that, hypothetically, in principle, within the framework of special relativity, a crew aboard a ship moving sufficiently close to the speed of light could traverse enormous distances in reasonable crew time, even if thousands or millions of years passed in Earth's reference frame. This does not violate the speed limit. From any observer's point of view, the ship is moving slower than light. But from the crew's perspective, due to time dilation, they can reach distant destinations within a human lifetime. At 99.9999% of the speed of light, the gamma factor, the time dilation multiplier, is approximately 707. This means 1 year of crew time corresponds to 707 years of Earth time. At this speed, a crew could reach Andromeda, 2.537 million light years, in approximately 3,585 years of their own time. This is still very long for a single lifetime, but in principle, with sufficiently exotic technology, crews of successive generations could, in principle, reach other galaxies, if only the universe allowed it. But the universe does not allow it, and here is why. Let us talk about the expansion of the universe. In 1929, Edwin Hubble showed that galaxies are receding from us, and the farther the galaxy, the faster it is receding. This does not mean Earth is the center of the universe and everything is fleeing from it. It means that space itself is expanding. The distances between galaxies are increasing as the spatial fabric stretches. This expansion behaves in a specific way. For galaxies far enough away, approximately beyond 4.4 billion light years from us, the apparent recession velocity exceeds the speed of light. This does not violate special relativity. Special relativity limits the speed of objects moving through space. The recession of galaxies is the expansion of space itself. There is no object moving through space faster than light. The space between us and these galaxies is simply increasing faster than light can cross it. The practical consequence of this is stark. For any galaxy currently located beyond approximately 4.4 billion light years, and this is a huge fraction of the observable universe, the space between us and it is expanding faster than light can cross it. This means light emitted by these galaxies right now will never reach us. And similarly, light we emit right now will never reach them. We cannot interact with these galaxies, not informationally, not physically. The boundary beyond which this is true is called the Hubble Event Horizon. But this is only the beginning of the story. The situation is actually worse. Let us talk about dark energy. In 1998, two independent research teams were studying distant Type 1a supernovae, a specific type of stellar explosion astronomers can use as standard candles, meaning objects of known luminosity that allow distance measurement. They expected to find that the expansion of the universe was slowing. Gravity from all the matter in the universe was expected to eventually halt the expansion, or reverse it. Instead, they found that the expansion of the universe is accelerating. This was one of the most shocking discoveries in the history of cosmology. It meant that there is some form of energy, now called dark energy, permeating all of space and acting like anti-gravity, causing space to expand faster and faster with time. The nature of dark energy remains one of the deepest unresolved questions in physics, but its implications for our future in the universe are concrete and verified. As the expansion of the universe accelerates, the Hubble event horizon, the boundary beyond which galaxies are receding faster than light, is not static, it is contracting. More and more galaxies cross the event horizon and become physically unreachable, not just physically, but informationally. This means the observable universe, the region from which we can, in principle, receive information, is shrinking with time. In the far future, all we will ever be able to see is our local group of galaxies. Andromeda and a few dozen small satellite galaxies of the Milky Way and Andromeda. Everything else, the trillions of galaxies currently constituting the observable universe, will eventually disappear behind the event horizon, their light never reaching us again, their existence becoming, in principle, unobservable. This is happening right now, not in the distant future, now. Every second, galaxies cross the Hubble event horizon and disappear from reach forever. Let us now address the specific question of tonight. How far could humans ever really travel? To answer this, we need to separate the question into several levels. The first level, what is achievable with realistically improved technology on reasonable timescales, decades to centuries. The second level, what is achievable in principle with theoretically possible future technologies, nuclear fission, nuclear fusion, matter-antimatter annihilation. The third level, what is achievable with technologies that violate no known laws of physics but require understanding and capability we do not yet have. Sublight speed interstellar travel. And finally, what is completely unreachable under any circumstances, not due to technological limitations, but because of the structure of the universe itself. Let us begin with the first level. Within the next century or two, assuming sustained technological progress and political will, humanity could plausibly reach several targets in the solar system. Mars is the most likely near-term target. Several agencies and private companies are developing concrete plans for crewed Mars missions. The physics is understood. The engineering challenges are enormous, but in principle solvable. The journey takes months. Radiation exposure is significant. Gravity on Mars is about 38% of Earth's. The asteroid belt and Lagrange points are potential locations for resource extraction and permanent stations. Jupiter and its moons, especially Europa with its subsurface ocean and Io with its volcanism, could be reached by robots in the near term and by humans in the long term. The distance to Jupiter ranges from about 588 to 968 million kilometers, depending on orbital position. With current technology, about a year one way. Saturn and its moon Enceladus, venting material from its subsurface ocean that could be sampled, are farther. About 2 years one way with current technology. Uranus and Neptune, at the edge of the planetary solar system, would require multi-year journeys, even with improved propulsion. All of this lies within the reach of technologies we can rationally extrapolate from what currently exists. But all of it remains within our solar system, a tiny pocket of space in the immensity of the universe. For the second level, theoretically possible future technologies, let us examine what physics in principle allows. Nuclear pulse propulsion, a concept developed during Project Orion in the 1950s to 60s, involved using nuclear explosions for propulsion. Small nuclear bombs would be detonated behind the spacecraft, pushing it with the shock waves. Theoretically, this approach could reach speeds of a few percent of the speed of light. Nuclear fusion, if ever mastered as a propulsion source, could provide even greater speeds. The specific impulse of a fusion drive significantly exceeds chemical or nuclear pulse approaches. Matter-antimatter annihilation is theoretically the most efficient energy source. 100% conversion of mass to energy, compared to about 0.7% for fusion and fractions of a percent for fission. An antimatter drive could theoretically reach significant fractions of the speed of light. The problem, producing antimatter in practical quantities, currently requires more energy than it yields by an enormous margin. Solar sails, thin films of reflective material pushed by sunlight or by a powerful laser, require no fuel. The breakthrough Starshot project proposed accelerating tiny probes to 20% of the speed of light using a laser array. At 20% of the speed of light, the journey to Proxima Centauri would take about 20 years. None of these technologies exists in a form capable of carrying people. For humans, with their need for food, water, air, space, radiation shielding, medical care, psychological well-being, the requirements are vastly more complex. The third level, sub-light-speed interstellar travel with people aboard, runs into serious but not fundamentally prohibitive obstacles. Time. At 10% of the speed of light, the journey to Proxima Centauri takes about 42 years. This is feasible for one generation, though difficult. At 50% of the speed of light, about 8.5 years. At 90%, about 4.7 years, plus significant time dilation. Energy. The amount of energy required to accelerate a ship large enough to support human life to relativistic speeds is simply enormous. At 10% of the speed of light, the kinetic energy of a 1,000-ton ship is about 4.5 times 10 to the 20 joules, roughly 100 times annual global energy consumption. The interstellar medium. Traveling at sublight speeds, the ship collides with atoms and dust particles in the interstellar medium at enormous velocities. At 90% of the speed of light, even a single proton represents a significant radiation dose. This requires a massive forward shield. But none of these obstacles is fundamentally prohibitive. They are complex, expensive, technically extraordinarily difficult. But physics does not forbid them. So if we assume sufficiently advanced technology we cannot precisely envision but that violates no known physical laws, in principle humans could travel to other stars, possibly to other galaxies given sufficient time and use of time dilation. This brings us to the fourth level, the limit that is not technological but fundamental. And here the story becomes genuinely strange. Let us talk about the event horizon and what it means for the maximum achievable distance. We established that the expansion of the universe is accelerating. This means that an ever larger portion of the universe becomes permanently unreachable, not just physically, but informationally. Light from these regions will never reach us. But the question of the maximum achievable distance for travel is not simply about what we can observe. It is about where we can, in principle, physically go. This is a different question with a different answer. Physicists Lawrence Krauss and Glenn Starkman analyzed this question specifically. Assuming that the accelerated expansion of the universe continues, which seems inevitable given current observations, they calculated the maximum physically achievable distance. The result is surprising and specific. If a civilization began a journey right now, moving as fast as physically possible, in the limit infinitely accelerating, always maintaining the maximum possible speed, it still could not exit beyond a certain distance. The expansion of space would eventually outrun any movement through it. The maximum achievable distance is approximately 4.9 billion light-years from our current position. 4.9 billion light-years is a large number. It sounds enormous. But the observable universe is approximately 93 billion light-years in diameter. This means the maximum achievable distance is only about 5% of the observable universe in radius. The volume within 4.9 billion light-years of us constitutes roughly 0.003% of the volume of the observable universe. 99.997% of the observable universe, everything we can see, everything we know exists, is forever physically unreachable. Not because of technological limitations, because of the structure of the universe itself. And this is just the observable universe. The full universe, which the evidence suggests is much larger than the observable portion, is even less reachable. This is the answer to tonight's question. How far could humans really go in space? At maximum, in principle, with any conceivable technology that does not violate known physics, approximately 4.9 billion light-years. Beyond that, never. Not with better engines, not with more time, never. Because the universe is built this way. Let us talk about what makes this situation even stranger. About the fact that the boundary of the reachable is not static, it moves, and it moves in the wrong direction. Right now, in this second, galaxies are crossing the Hubble Event Horizon. They are receding from us faster than the speed of light due to the expansion of space, and light they emit right now will never reach us. They do not disappear instantly from our field of view. We can still see their light already in transit, but new light emitted by them from this moment forward will never get here. This process continues. Over time, an ever larger portion of the universe becomes informationally unreachable. The physicist Lawrence Krauss described what this means for a civilization in the far future. If a civilization existed sufficiently far into the future, say several trillion years from now, the universe observable to them would be completely different. Most galaxies we currently see would be behind the event horizon, beyond reach and beyond sight. A civilization in the far future looking at the sky would see only the local group, our Milky Way, merged with Andromeda into one large elliptical remnant, in complete isolation. If they had not inherited our current science, they would not know that the universe contains more than 2 trillion other galaxies. The evidence for expansion, the Doppler redshift from receding galaxies, would be gone. The cosmic microwave background would be undetectable, shifted to radio waves of such low energy as to be practically impossible to detect. They would conclude from their observations that the universe is static, that only one galaxy exists, that the Big Bang did not happen. All of this would be wrong, but they would have no access to the data that would show it to be wrong. We are fortunate, in a strict sense, to exist at this early stage, to still be able to see enough of the universe to infer its history and structure, to still be able to detect the cosmic microwave background, to still be able to measure the recession of galaxies. In trillions of years, this window will be closed forever. Knowledge about the universe, the ability to understand its real scale and history, is temporary. It exists only within a certain window in the universe's history. We live in that window. Let us now talk about the specific structure of what is reachable, about the concrete regions of the universe that fall within the 4.9 billion light-year limit and what they contain. Starting from nearest to farthest within the reachable volume, the local group, the gravitationally bound collection of galaxies to which the Milky Way belongs, about 54 galaxies in a volume roughly 10 million light-years across. The dominant members, the Milky Way and Andromeda, will merge in about 4.5 billion years. The total stellar content of the merged galaxy will be roughly 1.4 trillion stars. This is our permanent gravitational home, the one structure that remains bound to us regardless of expansion. Beyond the local group, the Virgo supercluster, thousands of galaxies in a volume about 110 million light-years across. Our local group sits near the outskirts of this structure, which itself is part of the larger Laniakea supercluster, spanning about 520 million light-years. Beyond Laniakea, other superclusters, filaments, walls of the cosmic web, all the way to the limit at 4.9 billion light-years. Within this volume, billions of galaxies, quintillions of stars, the resources and space for any story a civilization could ever conceivably write. Beyond 4.9 billion light-years, the remaining 99.997% of the observable universe, billions of galaxies, possibly trillions of life-bearing worlds, permanently closed. Now let us talk about the specific reason why the reachability horizon is slightly beyond the Hubble event horizon, because this distinction reveals something interesting about the physics. The Hubble event horizon, 4.4 billion light-years, is the distance at which recession velocity equals the speed of light right now. A galaxy exactly at this distance is receding from us at exactly the speed of light at this moment. But if you start moving right now and move very fast, you can briefly chase the horizon, because the horizon itself moves. The boundary at which recession equals the speed of light shifts as the expansion accelerates. A traveller starting right now and moving infinitely close to the speed of light could reach objects slightly beyond the current event horizon, because as they approach, and as those objects approach the horizon from outside, both motions combine. But the acceleration of expansion eventually makes the horizon uncatchable. This is why the maximum achievable distance of 4.9 billion light-years slightly exceeds the current event horizon of 4.4 billion light-years. The difference, 500 million light-years, is small in context, but it is real and measurable and depends on the specific rate of expansion and its acceleration. This means that the maximum achievable distance is not simply the current Hubble event horizon. It is a more subtle boundary, determined by the full dynamics of the expansion. The precise value depends on cosmological parameters we measure from observations, the Hubble constant, the density of dark energy, the density of matter. It is a calculated number based on data, not a rough estimate. Let us now talk about what time dilation does and does not do for the maximum achievable distance. We established earlier that time dilation potentially allows crews to traverse enormous distances in finite subjective time. At very high fractions of the speed of light, the gamma factor is large, and crew time is much shorter than coordinate time. But time dilation does not change the maximum achievable distance. Here is why. The limit arises because space itself is expanding. As a traveler moves through space, space in the direction of travel is also expanding. If the expansion is fast enough, if the galaxy being aimed at is receding faster than light, no finite gamma factor allows it to be reached. The space being crossed expands faster than it can be crossed. This is not about running out of time. It is about running out of reachable space. No matter how close to the speed of light you travel, no matter how dilated your subjective time, you cannot cross a region of space that is expanding faster than you can traverse it. At the current expansion rate and its acceleration, the maximum achievable distance of 4.9 billion light-years is the same whether you travel at 10% of the speed of light or 99.9999% of the speed of light. The limit is not a speed limit, it is a distance limit in an expanding universe. This is a specifically deep point. Even perfect technology, achieving arbitrarily close to the speed of light, does not change this limit. The limit is not about speed, it is about the geometry of expanding space-time. Let us now talk about the three distances that define our cosmological situation, because holding them together produces the full picture. The first distance is the Hubble Event Horizon, about 4.4 billion light-years. This is the boundary beyond which galaxies are currently receding faster than light. Light emitted by us now will never reach galaxies beyond this distance. Light emitted by them now will never reach us. The second distance is the maximum achievable distance, about 4.9 billion light-years. This is how far anything from Earth could ever physically travel, given unlimited time and arbitrarily good technology that does not violate physics. The third distance is the particle horizon, about 46 billion light-years. This is the current distance to objects whose light has reached us since the Big Bang, the observable universe, much larger than either of the previous two distances. The relationship between these three numbers tells the full story. We can see 46 billion light-years. We can, in principle, reach 4.9 billion light-years. We cannot send signals beyond 4.4 billion light-years or receive signals from beyond it. The seeing horizon is about 10 times the reaching horizon. We can observe in detail things we can never reach. We receive information from objects that are permanently physically inaccessible. This is a specific kind of knowledge about what is forever beyond reach. This asymmetry between seeing and reaching is one of the most unusual features of our cosmological situation. Most of what we know about the universe comes from objects we will never visit and never interact with. Our knowledge of the universe is largely knowledge about the unreachable. Let us now talk about what happens to the reachable volume over time, because the situation does not stay static. As the expansion of the universe continues to accelerate, the Hubble Event Horizon contracts, in the sense that more and more galaxies cross it. The reachable volume shrinks relative to the full observable universe. However, this shrinkage happens on timescales of billions of years. In any timescale relevant to human civilization, even millions of years, the change is negligible. There is another time horizon worth considering. Stars are dying. The material for forming new stars is being used up. The universe is slowly dimming. In trillions of years, the vast majority of stars will have burned out. Only the longest-lived red dwarfs will remain, and eventually they too will go dark. This places a different kind of temporal limit, not a limit on reachable distance, but a limit on accessible time. The opportunities that exist while stars are burning will not exist after they go dark. If humanity or its successors intends to expand to the stars, to use the resources and opportunities of the reachable universe, they must do so while stars still exist. The universe gives an enormous window of time for this, trillions of years before the last stars die, but not an infinite one. Let us now talk about what lies between our current position and the maximum achievable distance, about the ladder of steps that constitute the path from here to there. Step 1. Earth to the Moon, 384,000 kilometers, achieved in 1969. Travel time, 3 days. Our only actual extraterrestrial human experience. Step 2. Earth to Mars, 55 to 400 million kilometers, depending on positions. With current technology, 7 to 9 months one way. Planned for coming decades, not yet achieved by humans, achieved by robots. Step 3. The Solar System as a whole. Neptune's orbit, about 30 astronomical units, or 4.5 billion kilometers. The Oort cloud to roughly 100,000 astronomical units, or about 1.5 light years. With current technology, years to decades to the outer planets, thousands of years to the Oort cloud. Outer planets reached by robots. Nothing has reached the Oort cloud. Step 4. Nearest stars. Proxima Centauri at 4.24 light years. With current technology, 73,000 years. With theoretical fusion or antimatter technologies, possibly decades. At 10% of the speed of light, about 42 years, never achieved by any human spacecraft. Step 5. Our galaxy. The Milky Way is roughly 100,000 light-years in diameter. At 10% of the speed of light, about 1 million years in galactic time, much less in crew time due to time dilation. In principle, achievable with technology not violating known physics. Never achieved. Step 6. The local group. About 10 million light-years. Andromeda at 2.537 million light-years. In principle, achievable with even more advanced technologies and timescales. Never achieved. Step 7. Nearest galaxy clusters. The Virgo supercluster, about 65 million light-years, still in principle achievable, requires timescales comparable to the current age of the universe. Step 8. The reachability horizon, 4.9 billion light-years. In principle, achievable, in the sense that physics does not forbid the journey, but requires billions of years and technologies beyond what we can realistically discuss. Step 9 does not exist. Beyond 4.9 billion light-years, there is nothing that can be reached. Not because nothing exists there. Enormous structures do exist there, galaxies, possibly life, but because the expansion of space makes them permanently unreachable. This ladder from the Moon to the reachability horizon spans approximately 20 orders of magnitude in distance, from 384,000 kilometers to 4.9 times 10 to the 22nd power kilometers. Each step requires technologies qualitatively different from the previous one, and the last step, the horizon itself, is unreachable under any circumstances. Let us now talk about the specific cosmological history that produced this situation, about why we live in a universe with this particular structure. The universe began approximately 13.8 billion years ago in an extremely hot, dense state, the Big Bang. In the first fraction of a second, fundamental particles formed. In the first few minutes, protons and neutrons fused into the nuclei of hydrogen, helium, and tiny amounts of lithium, a process called Big Bang nucleosynthesis. For the first 380,000 years, the universe was too hot and dense for atoms to form. It was an opaque plasma. Then it cooled enough for electrons to combine with nuclei, forming neutral atoms. The universe became transparent. The light released at this moment is what we see today as the cosmic microwave background, the oldest light we can detect, coming from 380,000 years after the Big Bang, from objects now located at distances of about 46 billion light-years. For the first several billion years of the universe's history, the expansion was decelerating. Gravity was winning, slowing the expansion. The universe was denser then, and matter's gravity was stronger. Then something changed. About 5 to 6 billion years ago, the expansion began to accelerate. Dark energy, whatever it is, became dominant as matter spread thinner and its gravity weakened, while dark energy, apparently intrinsic to space itself, remained constant. From that point forward, the expansion has been accelerating. And the acceleration is what establishes the reachability limit. If dark energy did not exist, if the universe contained only matter, gravity would slow and possibly reverse the expansion. The reachability limit would eventually extend to the full size of the universe. In principle, everything would be reachable given sufficient time. If dark energy were much stronger, many times its current value, the expansion would accelerate so fast that even our own galaxy would be torn apart. A phenomenon called the Big Rip. We happen to live in a universe with a specific value of dark energy that creates a specific reachability limit. This is not a choice, it is simply what the conditions are. But understanding that the value could have been different, and that different values give different limits, helps appreciate how concrete our situation is. We are not in the worst possible universe in this sense. With stronger dark energy, the horizon would be much closer. We are also not in the best. Without dark energy, the full universe would be in principle accessible, given sufficient time. We are in a specific universe with specific parameters, and those parameters produce a specific limit. Let us now talk about the most immediate practical question that this limit raises, about what it means for the nature of intelligent life in the universe if it exists elsewhere. If other civilizations exist, and the observable universe contains enough stars to make this statistically plausible, then most of them are beyond the reachability limit. Not just beyond our current technological reach, beyond the fundamental physical limit for any interaction. This means that even if the universe is full of life, which we do not know but which is entirely possible, most of it will never interact with most other life. Not because of silence or indifference, because of physics. Only civilizations within roughly 4.9 billion light-years of us can potentially interact with us, send something or receive something from us. That is still an enormous volume of space, but it is a small fraction of the observable universe. And for that interaction, even in principle, technologies far beyond current capabilities are required, on timescales of millions of years. The universe is structured such that the overwhelming majority of possible life in it, if it exists, will never know about the existence of most other possible life. Not because of disconnection or indifference, because of the geometry of expanding space-time. Each civilization exists within its own reachability bubble. Neighboring bubbles may overlap if civilizations are close enough, but most civilizations, if they exist, are in principle permanently isolated from most others by the accelerating expansion of space. The universe, if full of life, is an archipelago of isolated bubbles, not a connected web. The physics prevents the connection. This is not a sentimental conclusion. It is the logical consequence of the same physics that produces the maximum reachable distance of 4.9 billion light-years. Let us now talk about what the specific numbers of our situation mean when placed against each other. The Milky Way is 100,000 light-years in diameter. The maximum achievable distance is 4.9 billion light-years. The ratio is about 49,000. We could, in principle, reach 49,000 Milky Way diameters from our current position. That sounds like a lot, and in absolute terms it is enormous. But the observable universe is 93 billion light-years in radius. The ratio between the observable radius and the achievable radius is about 19:1. We can see 19 times farther than we can ever reach. In terms of volume, since volume scales as the cube of distance, the reachable volume is roughly 4.9 over 46.5 cubed of the observable volume. That is about 0.3% of the observable volume in the most generous calculation, or 0.003% by another measure, depending on which comparison is made. These numbers illustrate the core asymmetry of our situation. We observe enormously more than we can ever physically access. The universe is visible to us in its vast extent, but physically accessible only in a tiny fraction of what we see. Let us now talk about something that is rarely given enough weight in discussions of this limit, about the fact that even the reachable volume contains resources and space that no realistic civilization could ever exhaust. 4.9 billion light-years in radius is an inconceivably large volume. The number of galaxies within this distance, in the billions. The number of stars, in the quintillions. The number of planets, likely larger. If any civilization ever genuinely spread through even a small fraction of this reachable volume, the resources and opportunities involved would be essentially unlimited by any measure meaningful to us now. Energy from stars, materials from asteroids and planets and interstellar space, time, billions of years while stars still burn. The limit is real. It constrains the infinite to the merely enormous. That is not a prison sentence. The more important limiting factors for any real civilization are not the cosmological event horizon, but the immediate practical challenges. Developing technology for interstellar travel, sustaining civilization over the timescales required, maintaining the motivation and continuity to pursue goals across generations and millennia. These are the real challenges. The physics sets a ceiling at 4.9 billion light-years. The actual limiting factors operate at scales many orders of magnitude closer to home. Let us now talk about something that lives at the very heart of this question, about the remarkable fact that we know this limit at all. We sit on a small planet. We have not travelled beyond the moon. Our fastest spacecraft barely exits the solar system in a human lifetime. And yet, from this position, we have determined that the maximum achievable distance is approximately 4.9 billion light-years. That 99.997% of the observable universe is permanently unreachable. That the expansion is accelerating. That dark energy is real. This knowledge was earned through centuries of astronomical observation, understanding stellar spectra, deriving distances, discovering that galaxies are receding, understanding the cosmology of an expanding universe, measuring the acceleration of that expansion from supernova data. Each step was an extraordinary achievement, and together they gave us a map of the reachable and the unreachable, a map that spans the observable universe and points to its limits. We know this before we have the technology to go anywhere. We have charted the boundaries of the achievable before approaching them. This is a specifically human achievement, to know more than we have reached, to understand space we have not visited, and that knowledge, concrete, numerical, grounded in measurements, tells us something real about the structure of reality, about how space and time and their expansion define what is possible. Tonight, while you look at the sky, every glowing point, every faint smear of the Milky Way, every barely visible patch of light that might be another galaxy, carries this knowledge within it. Most of the visible stars nearby in our galaxy are in principle reachable. Those faint smudges that might be galaxies, some reachable, most not. The darkness between, full of galaxies too faint to see without a telescope, most of them forever beyond reach. This is the map, real, physically grounded, derived from data. We are at one small point on this map, at the beginning of a possible journey, with a limit fixed at the end. Between here and the limit, everything that is possible. Beyond the limit, forever closed. Let us talk about something that requires a specific kind of attention, about the concrete history of how we discovered that the expansion of the universe is accelerating, and why the precision of that discovery matters for the credibility of the limit. The discovery happened in 1998. Two independent teams, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were both using Type 1a supernovae as distance indicators to measure how fast the universe's expansion was changing. The underlying principle is elegant. Type 1a supernovae are produced by a specific physical process. A white dwarf in a binary system accumulates mass from a companion until it reaches a critical threshold of about 1.44 solar masses and explodes. Because the trigger mass is always the same, the explosion always produces approximately the same amount of energy. By measuring how bright the supernova appears, and knowing how bright it actually is, you can calculate how far away it is with considerable precision. Both teams expected to measure a deceleration. The gravitational pull of all the matter in the universe should be slowing the expansion. The question was only whether the deceleration was strong enough to eventually halt the expansion and reverse it, or whether the universe would expand forever, but more and more slowly. What they found instead was that distant supernovae appeared dimmer than they should be, not because they were intrinsically fainter, but because they were farther away than the decelerating expansion models predicted. The expansion was not slowing down, it was speeding up. Both teams spent considerable time checking for systematic errors before publishing. Dust that might make the supernovae appear dimmer, evolution of the supernovae themselves over cosmic time that might change their intrinsic brightness, gravitational lensing effects, selection biases in how the supernovae were detected. None of these could explain the result. The acceleration was real. The discovery earned Perlmutter, Schmidt and Rees the Nobel Prize in Physics in 2011. Since 1998, the result has been confirmed from completely independent sources. Measurements of the cosmic microwave background from the WMAP and Planck satellites. The distribution of galaxies in large-scale structure surveys. Baryon acoustic oscillations. Sound waves in the early universe that left an imprint in the galaxy distribution. gravitational lensing surveys. Every independent method points to the same conclusion. The expansion is accelerating. Dark energy is real. The event horizon is real. The reachability limit is real. This is not one observation interpreted one way. It is the convergence of many independent lines of evidence, all pointing in the same direction. This is why physicists take it seriously. And this is why the reachability limit of 4.9 billion light-years is not speculation, but a concrete consequence of well-confirmed physics. Let us now talk about what dark energy actually is, or rather, what we do not know about it, because the nature of our ignorance here matters. Dark energy is a placeholder. It is the name we give to something we observe but do not understand. We observe the effect, the acceleration of expansion, but we do not know the mechanism. The simplest explanation is the cosmological constant, a term Einstein introduced into his equations of general relativity in 1917, originally to produce a static universe. When Hubble discovered the expansion, Einstein removed it, calling it his greatest blunder. The irony is that it turned out to be needed, but for a different reason than he intended. The cosmological constant can be interpreted as the energy of the vacuum itself, the energy of empty space. Quantum mechanics predicts that empty space should have a non-zero energy due to virtual particles and quantum fluctuations. The problem, the theoretically calculated vacuum energy from quantum field theory, is roughly 10 to the power of 120 times larger than the observed dark energy. This is the largest discrepancy between theory and observation in the history of physics. Understanding why the observed value is so small is one of the major unsolved problems in theoretical physics. There are other explanations for dark energy. Quintessence, a dynamic scalar field that slowly evolves over time. Modified gravity, alterations to general relativity on cosmological scales, and others. What matters for the reachability limit is the following. If dark energy is not a constant but a slowly changing field, the limit might differ slightly from 4.9 billion light-years. If dark energy weakens over time, the expansion might slow and the limit would shift outward. If it strengthens, the limit would contract. Current data are consistent with a constant dark energy, the cosmological constant, to within a few percent. There is no compelling evidence that it changes, but there is no absolute certainty either. This is the honest uncertainty. The limit of 4.9 billion light-years is our best current value based on our best current physics. It may be refined as measurements improve and understanding of dark energy deepens. But the qualitative conclusion that accelerated expansion establishes a finite, hard reachability horizon is robust across a wide range of dark energy models. The limit is real, even if its precise value is subject to revision. Let us now talk about the specific physical mechanism that establishes the limit in more detail, because understanding this mechanism is what distinguishes the reachability limit from a merely practical limitation. Imagine a spaceship departing from Earth right now and accelerating toward a galaxy currently located at the edge of the reachability limit, about 4.9 billion light-years away. As the ship travels, the space between the ship and the destination continues to expand. The ship is moving through space toward the destination, but space itself is expanding in the same direction, adding distance between the ship and the destination. The two effects, the ship's motion and the expansion of space, operate simultaneously. If the ship is moving close enough to the speed of light, its motion can outpace the expansion for galaxies within the reachable limit. The ship can reach those galaxies because the rate at which it closes the distance is faster than the rate at which expansion adds to it. But beyond the reachability horizon, for galaxies more than 4.9 billion light-years away, the expansion of space adds distance faster than any possible motion can close it. This is not because those galaxies are moving through space faster than light. It is because space between us and them is expanding, growing, at a rate that no physical motion can overcome. The critical insight is that this is not about running out of time. It is not that the journey takes too long. It is that the destination recedes faster than it can be approached, permanently, regardless of how fast the ship moves or how long the journey continues. A ship aimed at a galaxy beyond the reachability limit would find the galaxy perpetually moving away. No matter how much the ship accelerates, the gap does not close. The ship could travel for 1 billion years and the destination would still be unreachable, not because the ship is not fast enough, but because the expanding space is adding distance faster than the ship can traverse it. This is a fundamentally different kind of limit from, say, a speed limit. It is a limit on which destinations exist in the physically accessible universe, given the geometry of expanding spacetime. Let us now talk about the remarkable asymmetry between the three distances: the particle horizon, the event horizon, and the reachability horizon, and what this asymmetry tells us. The particle horizon, approximately 46 billion light-years, is how far we can see. It represents the maximum distance from which light has reached us since the Big Bang. This is the largest of the three distances. The reachability horizon, approximately 4.9 billion light-years, is how far we can physically travel. This is about 10% of the particle horizon. The Hubble event horizon, approximately 4.4 billion light-years, is the current boundary beyond which space is expanding faster than light. This is slightly smaller than the reachability horizon because, as we established, a ship moving at close to the speed of light can briefly outpace the event horizon before the accelerating expansion catches it. We can see 10 times farther than we can ever reach. We receive information from objects that are permanently physically inaccessible. The visible universe and the reachable universe are not the same thing. They are dramatically different things. This asymmetry is not an accident. It arises from the specific physics of an expanding universe with a finite age and an accelerating expansion rate. In a universe without dark energy, with only decelerating expansion, the reachable volume and the observable volume would both grow over time and would be more comparable. In our universe with dark energy causing acceleration, the reachable volume is permanently smaller than the observable volume. We are cosmological observers in a larger universe than we can inhabit. The universe shows us things we can never touch. There is something philosophically specific about this situation. Our knowledge of the universe extends far beyond our physical reach. The boundary of knowledge is much farther than the boundary of presence. We understand regions of space-time, their composition, their history, their distance, that we will never visit and never interact with. This kind of knowledge about what is permanently beyond reach, is unusual. Most knowledge is at least potentially actionable. We know how to build bridges and we can build them. We know how to cure diseases and we can cure them. But the knowledge that 99.997% of the observable universe is permanently inaccessible is knowledge about what we cannot do, knowledge about limits. It is still worth having. It tells us something real about the structure of the reality we inhabit. Let us now talk about what the reachability limit means for the long-term future. For for civilizations thinking not in decades or centuries, but in billions of years. On the timescale of billions of years, a civilization that has mastered sub-light speed travel could, in principle, spread through the reachable volume. The Milky Way, 100,000 light-years in diameter, could be crossed in about 1 million years at 10% of the speed of light. The local group, 10 million light-years, in about 100 million years at the same speed. The reachability horizon at 4.9 billion light-years would take billions of years to approach, even at a significant fraction of the speed of light. But there is no physical prohibition on the journey. What would such a civilization find in the reachable volume? The same structures we observe from here: galaxies, stars, planetary systems. If life arises wherever conditions permit, those structures potentially contain other civilizations. If they do not, they contain enormous resources and space. The reachable volume is not homogeneous. There are regions of higher galaxy density, clusters and superclusters, and regions of lower density, cosmic voids. A civilization spreading through the reachable volume would encounter this structure, some regions rich with stellar material, others nearly empty. The timescales involved are astronomical, many billions of years from beginning to any meaningful completion. The age of the universe is currently 13.8 billion years. A full traversal of the reachable volume would take a comparable length of time. In that time, the universe itself changes. Stars that currently burn will have exhausted their fuel. New stars will have formed. The cosmic microwave background will have redshifted further. The surviving galaxies beyond the reachability horizon will have receded further. The universe will look different, quieter, emptier than it does now. This is the context of any truly long-term civilizational future, not just spreading across space, but doing so in a universe that is itself changing, cooling, dimming, spreading. Let us now talk about something that is rarely included in these discussions, about the connection between the reachability limit and the question of what our existence means in a cosmological context. There is a specific character to knowing that we exist in a part of the universe that represents a small fraction of the whole, that the overwhelming majority of what exists is permanently beyond our reach, while simultaneously knowing that the part we inhabit contains billions of galaxies and quintillions of stars. This combination, the vastness of what is accessible and the even greater vastness of what is not, produces a specific kind of orientation. We are not cosmically central. The observable universe contains no privileged location. Our galaxy is not special. Our solar system is not special. Our planet, though special to us, is not cosmologically special. And yet we are not insignificant in the sense of being without consequence. Something happened here, on this planet, around this star, in this galaxy, that allows the universe to understand itself. The atoms in a human brain include atoms forged in the cores of massive stars, blown into space in supernova explosions, condensed into a solar system, assembled by 4 billion years of biological evolution into structures capable of understanding their own history. Understanding the reachability limit, knowing what the universe allows and what it does not, is part of this self-understanding. The universe, in the inaccessible 99.997%, does not know its own structure as far as we know. The part of the universe that we inhabit contains at least one example of something that does. This does not make us the center of anything. It makes us, or at least our presence here, cosmologically interesting, if not cosmologically privileged. Let us now talk about what happens on timescales much longer than stellar lifetimes, about the very distant future, and what the reachability limit means for it. On timescales of trillions of years, the universe enters what physicists call the degenerate era. The last red dwarf stars, the most long-lived stars, exhaust their fuel and go dark. The universe no longer illuminates itself from within. What remains after stellar death are white dwarfs slowly cooling to invisibility, neutron stars, black holes, and the cold remnants of planetary systems and interstellar debris. On even longer timescales, quadrillions to quintillions of years, protons themselves may decay, if proton decay happens at all. Atomic matter gradually dissolves. Eventually, on unimaginably long timescales, even black holes evaporate through Hawking radiation, one by one, the largest ones last. What is left after all of this is a universe of extreme low energy, a thin scattering of photons, electrons, positrons and neutrinos in an essentially infinite volume of cold, dark space. Through all of this, through the death of stars, through the evaporation of black holes, the expansion continues. The reachability limit, in a sense, becomes irrelevant because there is progressively less to reach for and less energy to make the journey. The window of meaningful expansion, the window during which there are stars and resources and destinations worth reaching, is finite. It spans from now until roughly the death of the last red dwarfs, perhaps 10 to 100 trillion years in the future. That is an enormous window, but it is not infinite. In that window lies everything that is possible in the reachable universe. The window is open now. Let us now talk about the most direct and concrete implication of everything discussed tonight, about what understanding the maximum reachable distance changes in how you look at the night sky. The stars you see are in the Milky Way, within tens to a few hundred light years, in principle reachable, unreachably far by current technology. But physics does not forbid the journey. The Andromeda Galaxy, if you know where to look, a faint patch slightly above the constellation Andromeda in the northern sky, is 2.537 million light-years away, also in principle reachable. Much farther, but within the reachability horizon. The galaxies visible through telescopes, hundreds, thousands, millions, billions of light-years away, some reachable, most not. The transition from reachable to unreachable happens around 4.9 billion light-years. Objects beyond that are visible to our telescopes but permanently inaccessible. The darkness between the stars, full of galaxies too faint to see without instruments, mostly unreachable. That darkness contains the overwhelming majority of what exists in the observable universe. This is what the night sky is, viewed through the lens of the reachability limit. A small portion, the visible stars, is reachable in principle. A somewhat larger portion, the nearest galaxies, also in principle reachable. The vast majority, the trillions of galaxies beyond 4.9 billion light-years, permanently closed. We happen to be in the reachable portion. The part of the universe that contains us is also the part from which we originated and to which our possible future is limited. Not because of anything special about us, because this is where we started, and the physics of the expanding universe establishes a limit from any starting point. That limit, wherever you are in the universe, is roughly the same size, about 4.9 billion light-years in radius from your location, given the current value of dark energy. Everywhere in the universe, in every galaxy, around every star, on every planet that might have life, the same physics applies. The same limit, the same permanent closure of most of the observable universe from physical access. The universe is built this way, not for us or against us, just built this way. And knowing it is built this way, knowing the size of the accessible portion, knowing where the permanent boundary is, knowing the physics that establishes it, is itself one of the more remarkable things that has happened anywhere in the universe that we know of. A small planet in a small part of the reachable universe figured out the size of the reachable universe. That is where we are tonight. Let us talk about something that requires a specific kind of patience, about the relationship between what we can imagine and what physics allows, and how these two things are not always the same. Human imagination about space travel tends towards the unlimited. Science fiction has conditioned us to think of the universe as explorable in its entirety, faster than light travel, warp drives, hyperspace, jump drives. These are not merely entertaining fantasies. They reflect something deep about human psychology. We want the universe to be accessible. We want there to be no permanent limits. The physics says otherwise. But the interesting question is not whether the physics says otherwise, it clearly does, but what it means to hold both things simultaneously. The desire for an unlimited universe and the knowledge that the universe is limited in a specific and irreversible way. This is not a new experience. Human history is full of encounters with real limits that previously seemed negotiable. We cannot move faster than light through space. We cannot observe the interior of a black hole from outside. We cannot know both the position and momentum of a particle simultaneously below the Heisenberg limit. We cannot extract useful work from a system at thermal equilibrium. Each of these limits was discovered through the same process: careful observation revealing that something previously imagined as possible is in fact forbidden by the structure of reality. The cosmological reachability limit is the same kind of discovery. The universe does not permit access to its full extent, not because of any limitation in us, but because of the geometry of expanding spacetime. The appropriate response to this, the intellectually honest response, is neither disappointment nor forced acceptance. It is the specific satisfaction of knowing something real. This is what physics at its best does. It tells us what is real and what is not. It draws a line between what the universe allows and what it does not. And knowing that line, even when the line is a constraint, is more valuable than not knowing it. Let us now talk about something more concrete, about what the existence of the reachability limit implies for the kind of universe we inhabit, and how this compares with alternatives. We can imagine universes with different properties. A universe without dark energy would not have an accelerating expansion. In such a universe, the reachability limit would be much farther. Possibly the entire observable universe would be in principle accessible, given sufficient time. There would be no fundamental horizon of the kind we have been discussing. The universe would still be vast, and the travel times still astronomical, but there would be no permanent closure of portions of it. A universe with stronger dark energy, say 10 times the current value, would have a smaller reachability limit. The event horizon would be closer. Less of the observable universe would be accessible. In the extreme, a universe with very strong dark energy would undergo a big rip, the accelerating expansion eventually tearing apart galaxies, then stars, then planets, then atoms. A universe with much weaker dark energy, nearly zero, would expand more slowly and possibly eventually halt and reverse, collapsing in a big crunch. We happen to inhabit a universe with a specific value of dark energy that places the reachability limit at about 4.9 billion light-years. This value is neither the best possible, a universe without dark energy would be more accessible, nor the worst possible. Stronger dark energy would be more constrained. Why does our universe have this particular value of dark energy? This is one of the deepest unsolved questions in physics. The cosmological constant problem, explaining why the vacuum energy density is what it is, rather than 10 to the power of 120 times larger, as quantum field theory predicts, has no accepted solution. Some physicists invoke the anthropic principle, the idea that we observe this value because a much larger value would not have allowed galaxies and stars and planets and us to form in the first place. If dark energy were much stronger, structure would not have formed. We could only observe a universe compatible with our existence. This argument is contested. But the observation is correct that our particular value of dark energy falls in the range that permits structure formation and therefore permits observers. What matters for tonight is simpler. Whatever the explanation for the value of dark energy, the value is what it is. It produces the universe we observe. And the universe we observe has a reachability limit of approximately 4.9 billion light years. We did not choose this universe. We did not set the parameters, but we live in it and we can understand it. Let us now talk about an aspect of the reachability limit that is often underappreciated, about what it implies for the search for extraterrestrial intelligence. The search for extraterrestrial intelligence, SETI, is premised on the assumption that if other technological civilizations exist, they might emit electromagnetic signals detectable from Earth. Radio waves, laser pulses, other structured electromagnetic radiation. The reachability limit does not directly constrain what we can detect. Electromagnetic signals travel at the speed of light, and the particle horizon, the boundary from which we can receive light, extends to about 46 billion light years. So in principle, we could detect signals from civilizations anywhere in the observable universe. But the reachability limit places a constraint on something more fundamental, the prospect of any physical interaction, any exchange of material or travel with those civilizations. Even if we detect a signal from a civilization 10 billion light years away, well beyond the reachability horizon, we could never physically reach them, and they could never physically reach us. Any communication would be strictly one way, or, at best, a very long exchange of messages, with response times measured in billions of years. And for civilizations beyond the event horizon, beyond 4.4 billion light years, even signal exchange is permanently impossible. Any message we send now will never reach them. Any message they send now will never reach us. This means that the universe is structured such that most possible civilizations, if they exist, spread as they might be across the observable universe, are permanently incommunicado. Not just difficult to contact, principally impossible to contact or visit. The universe is built such that most of its possible inhabitants are isolated from most of its other possible inhabitants by the geometry of expanding spacetime. This has implications for how we should think about the cosmic context of intelligent life. If we imagine a universe teeming with civilizations, billions of them spread across the 2 trillion galaxies of the observable universe, most of those civilizations would be permanently unaware of most others. Each exists in its own bubble of reachability, with a horizon beyond which no interaction is possible. Only civilizations within each other's reachability bubbles, separated by less than about 4.9 billion light years, can in principle interact. For the universe as a whole, this is a small fraction of possible civilization pairs. The universe, if it is full of life, is not a connected web. It is a collection of isolated islands. The physics ensures this. Let us now talk about how the discovery of this limit changes our understanding of what kind of universe we inhabit, compared to what we might naively expect. Before the discovery of the accelerating expansion in 1998, the cosmological picture was simpler in one sense. The universe was expanding. The expansion was expected to slow. In principle, given infinite time, more and more of the universe might become accessible as light from ever more distant regions accumulated enough time to reach us. The accelerating expansion changed this fundamentally. It introduced a permanent horizon, a boundary that does not shrink over time, a boundary beyond which the universe is permanently closed. This was not anticipated. It required a new component of the universe, dark energy, with properties unlike anything previously identified. It required a conceptual shift in what kind of universe we inhabit. Before 1998, the universe was large, but in principle accessible over infinite time. After 1998, the universe is large, but in significant part permanently inaccessible regardless of time. This is a qualitative shift in the nature of our cosmological situation, not just a quantitative change in the numbers, a change in what the universe is at a fundamental level. The universe went from being, in principle, explorable in its entirety to being, in principle, explorable only in part. A small part, as we have seen, about 0.003% of the observable volume. That shift happened 25 years ago. We are still absorbing its implications. Let us now talk about something that connects the maximum reachable distance to questions of meaning, about what it means to exist in the accessible portion of a larger, inaccessible universe. There are at least two ways to hold this knowledge. The first is as a constraint. We are limited. Most of the universe is closed to us. We inhabit a small fraction of the whole. The vast majority of what exists is permanently beyond reach. The second is as a context. The portion we inhabit, though small relative to the whole, is not small in absolute terms. It contains billions of galaxies, quintillions of stars, and timescales stretching to trillions of years. The limit constrains the infinite to the merely enormous. Which framing is more accurate depends on what you are comparing to. Relative to the full observable universe, the reachable portion is tiny. Relative to anything we have ever known, the reachable portion is incomprehensibly vast. What remains fixed regardless of framing is the physics. The limit exists. It is real. It was discovered through careful measurement and is confirmed by multiple independent lines of evidence. And knowing this limit, knowing it precisely, grounding it in data, understanding the physics that produces it, is itself an achievement, one that places us in a specific and concrete relationship with the universe we inhabit. We know where the walls are. We know the size of the accessible space. We know, in principle, the territory available for any future that might unfold from this planet. That is not nothing. That is a map. Let us now talk about what the future of measuring this limit looks like, about how our knowledge of the reachability horizon might become more precise. The primary uncertainty in the 4.9 billion light-year figure comes from uncertainty in the nature of dark energy, specifically whether it is truly constant or whether it evolves over time. Current measurements constrain dark energy to be close to a cosmological constant with an uncertainty of a few percent. But this uncertainty matters for the precise value of the reachability limit. Future observational projects aim to measure dark energy with much greater precision. the Vera Rubin Observatory, currently beginning operations, will survey billions of galaxies and measure cosmic structure to unprecedented precision. The Euclid Space Telescope, launched in 2023, is specifically designed to constrain dark energy through measurements of galaxy clustering and gravitational lensing. The Nancy Grace Roman Space Telescope, planned for later this decade, will complement these with additional supernova measurements. These projects will narrow the uncertainty in the equation of state of dark energy, the parameter describing how dark energy's density might change over time. A more precise measurement of this parameter would translate to a more precise value of the maximum reachable distance. It will not change the qualitative conclusion that the reachability limit is real and that most of the observable universe is permanently inaccessible, but it will sharpen the number. Instead of about 4.9 billion light-years, we might eventually know the value to within a fraction of a percent. This precision matters not just for the practical question of the reachability limit, but for fundamental physics, for understanding what dark energy is, which remains one of the deepest open questions in science. The irony is worth noting. We will never be able to test the reachability limit directly by actually attempting to travel to the horizon. The timescales are billions of years, and the technology does not exist. We will refine our knowledge of the limit through observations made from Earth, through telescopes pointed at distant galaxies, measuring the subtle statistical properties of their distribution. Knowledge of the unreachable obtained from here. Let us now talk about something that puts the maximum reachable distance in the broadest possible context, about what this limit tells us about the nature of knowledge itself in a physical universe. Physics is often described as the search for universal laws, laws that apply everywhere in the universe, at all times, under all conditions. The speed of light is the same everywhere. The laws of thermodynamics apply universally. Quantum mechanics governs physics at the small scale, regardless of location. But the universe also has boundaries on knowledge, places where our understanding cannot be extended by observation, because observation is physically impossible. The interior of a black hole, beyond the event horizon, is not accessible to outside observers. The region beyond the cosmological event horizon is not accessible to us. These are not gaps in our theory. They are features of the structure of space-time that limit what can in principle be known from any given location. The reachability limit is a related but distinct boundary. It does not limit what can be known. We can observe far beyond the reachability limit through telescopes, but it limits what can be physically reached or interacted with. This creates a universe in which knowledge and access are decoupled. We know about regions of space-time we cannot visit and cannot interact with. We understand their physics, their composition, their distance, their history, but we cannot go there and we cannot affect them. This is a specific and unusual epistemic situation. In ordinary life, knowledge tends to enable action. We know how to build a bridge and we can build it. We know how to cure a disease, and we can treat it. Knowledge and capability tend to go together. But in cosmology, knowledge of the unreachable is possible and real. We know the size of the reachable universe. We know what lies beyond it. We know that it is permanently inaccessible. This knowledge does not enable action, not in the relevant domain. There is nothing to do with the knowledge that the universe beyond 4.9 billion light-years is unreachable, except understand it. But understanding it is valuable, not because it enables action, but because it tells us something true about the structure of reality. And that, the pursuit of what is true about the structure of reality, regardless of whether the knowledge enables action, is the deepest version of what science is. Let us now talk about one final concrete aspect of the reachability limit, about what it means for the universe's long-term fate and the place of intelligence within it. We established that in the very distant future, trillions of years from now, the last stars will burn out. The universe will become dark. The reachable volume will continue to expand, but there will be progressively less to reach within it. Fewer active stars, fewer sources of energy, fewer hospitable environments. Any civilization that exists in the far future will face a universe not of abundance, but of scarcity. The raw material for stellar formation will be exhausted. Energy must be extracted from increasingly diffuse sources, cooling white dwarfs, orbiting compact objects, eventually the slow evaporation of black holes. In this context, the question of how far a civilization can travel becomes less about distance and more about time. The hard constraint is not the spatial extent of the reachable volume, but the available time before the energy sources that enable travel are exhausted. The universe gives an enormous window, but the window has two ends. A beginning, when the first stars ignited. An end, when the last sources of energy dissipate. We exist very early in this window. The universe is 13.8 billion years old. The window of stellar energy extends perhaps 100 trillion years into the future. We are in the first tiny fraction of the accessible window. This means that any future the universe has for intelligence, if intelligence persists, extends almost entirely ahead of us. The vast majority of the time during which the reachable universe contains energy and structure is in the future, not the past. We are at the beginning of what is possible. Not the beginning of the universe, that was 13.8 billion years ago, but the beginning of what intelligence might do within the reachable universe, within the window of time during which that universe supports complex structures and activities. The reachability limit closes off most of space, but time, the other dimension of the accessible universe, is mostly still ahead. This is where we are tonight, in the reachable portion of the universe, in the early part of the accessible window of time, with a map of the accessible space and a sense of its extent, with no guarantee of any particular future, but with the physical possibility of one. The stars above you tonight are, most of them, in our galaxy, part of the accessible portion, part of the window. The limit is about 4.9 billion light years out, beyond what any telescope can resolve with the naked eye, beyond what any human has experienced directly, but known, calculated, confirmed by multiple independent measurements. This is what we know about how far humans could really go in space. Let us talk about something that sits at the intersection of physics and human psychology, about why the existence of the reachability limit feels different from other physical limits, and what that difference reveals. Most physical limits we encounter in daily life are limits of scale or complexity. The bridge will hold this much weight, but not more. The engine produces this much power, but not more. These are engineering limits, real, but in principle subject to improvement with better materials, better design, more resources. Even the speed of light, the fundamental speed limit of the universe, feels different from the reachability limit in an important way. The speed of light is a limit on how fast you can go, but within that limit, the entire universe is in principle addressable. If you could travel at the speed of light, in principle you could aim for any galaxy you can see. The reachability limit is different in character. It is not a limit on how fast you can go. It is a limit on which destinations exist in the physically accessible universe, regardless of speed. The unreachable regions are not unreachable because we cannot go fast enough. They are unreachable because the space between us and them is expanding faster than any possible traversal. This means the unreachable regions are not destinations at all in any meaningful physical sense. They are observable features of a universe that extends beyond the domain any physical process originating here can affect. Think about what this means for a moment. When we observe a galaxy 50 billion light-years away through a telescope, we are seeing something real. Light genuinely travelled from that galaxy to our instruments. Photons that originated there are landing on our detector right now. In that sense, the galaxy is present to us. We are receiving its message. But that galaxy, and we, exist in what are essentially different universes in the sense that matters most for causality. No physical effect originating here can ever reach that galaxy. No physical effect originating there can ever reach us. We are causally disconnected, permanently, regardless of what either of us does. The light that reached us left that galaxy billions of years ago, before our solar system formed. In the time that light has been travelling, the universe has expanded so much that the galaxy is now far beyond the causal horizon. We see its past. Its present and future are permanently inaccessible, even to light. This is a specific and unusual kind of relationship with an object. We observe it, we measure it, we understand it, we name it and catalogue it, and we have absolutely no causal connection with its present or future state. This is what the reachability limit and the broader cosmological horizon structure means in the most concrete terms. A large fraction of what we observe is causally disconnected from us, permanently. Let us now talk about the specific numbers involved in the current observable universe more carefully, because getting these right is important for understanding the true scale of what is accessible and what is not. The observable universe has a radius of approximately 46.5 billion light-years. This is the co-moving distance to the particle horizon, the current distance to objects whose light has been travelling toward us since shortly after the Big Bang. It is larger than 13.8 billion light-years, the age of the universe in years, because the universe has been expanding while that light was in transit. Within this observable sphere, there are estimated to be approximately 2 trillion galaxies. The most recent estimates, refined from Hubble Deep Field observations and extrapolations of galaxy number density at different epochs, suggest this figure, though with significant uncertainty. 2 trillion galaxies, each containing, on average, hundreds of billions of stars. The total number of stars in the observable universe is estimated at roughly 10 to the 24th power, a septillion. More stars in the observable universe than grains of sand on all the beaches and deserts of Earth. Of these 2 trillion galaxies, how many are within the reachable volume? The reachable volume has a radius of about 4.9 billion light-years, compared to the observable radius of about 46.5 billion light-years. The ratio of volumes is 4.9 over 46.5 cubed, which is approximately 0.00117, about 0.12%. If galaxies were uniformly distributed, which they are not, but as a rough estimate, about 0.12% of 2 trillion galaxies would be within the reachable volume. That is roughly 2.4 billion galaxies. 2.4 billion galaxies, each with hundreds of billions of stars. The total number of stars in the reachable volume is still an astronomically large number, on the order of 10 to the 21st power or more. This is what is accessible, not a small number in any absolute sense, but about 0.12% of the observable total. The remaining 99.88%, roughly 1.997 trillion galaxies, are permanently physically inaccessible. These are not rough estimates. They follow from specific measured values: the Hubble constant, the dark energy density, the matter density, that cosmologists have measured to considerable precision using multiple independent methods. Let us now talk about what it actually took to make these measurements, about the history of cosmological observation that led to knowing the reachability limit with the precision we have. The story begins with Henrietta Swan Leavitt, an astronomer at Harvard who in 1908 and 1912 discovered a relationship between the period of variation and the luminosity of Cepheid variable stars. Cepheids pulsate. They brighten and dim over periods of days to weeks. Leavitt found that the longer the period, the more luminous the star. This relationship, the period luminosity relationship, gave astronomers a way to measure distances to objects containing Cepheid stars. Edwin Hubble used Leavitt's Cepheid relationship in the 1920s to show that certain nebulae, fuzzy patches of light that some astronomers thought were nearby gas clouds, were actually distant galaxies far outside the Milky Way. The Andromeda Nebula, Hubble showed, was about 900,000 light-years away. The modern value is 2.537 million light-years, but Hubble's measurement established the crucial point that it was outside our galaxy. Hubble then measured the recession velocities of galaxies from their redshift, the stretching of light toward longer wavelengths as the source moves away. Combining distance measurements with recession velocities, Hubble found the relationship that bears his name. The farther the galaxy, the faster it recedes. Published in 1929, this established the expanding universe. For the next several decades, astronomers refined these measurements. The Hubble constant, the rate of expansion, proved difficult to pin down precisely. Early estimates ranged from 50 to 100 kilometers per second per megaparsec. Understanding whether the expansion was slowing down or had slowed down sufficiently to eventually reverse became a primary goal of cosmological research. The supernova studies of the 1990s, culminating in the 1998 discovery of accelerating expansion, required measuring very distant supernovae with precision sufficient to detect the difference between decelerating and accelerating models. This required the Hubble Space Telescope and careful characterization of potential systematic errors. The subsequent decades of cosmic microwave background measurements, from the COBE satellite in the early 1990s through WMAP and then Planck, provided completely independent constraints on the cosmological parameters. The CMB acts as a snapshot of the universe at 380,000 years old. Its detailed pattern of temperature fluctuations encodes information about the composition of the universe, the fractions of ordinary matter, dark matter, and dark energy, with extraordinary precision. The current best values from combining multiple cosmological probes, the Hubble constant, approximately 67 to 73 kilometers per second per megaparsec, with a tension between different measurement methods that remains one of the active research questions in cosmology. The dark energy density, consistent with a cosmological constant with density parameter of approximately 0.68, meaning dark energy constitutes about 68% of the total energy content of the universe. The matter density, about 0.27% ordinary matter, and about 27% dark matter, together constituting about 32% of the total energy content. These parameters together determine the geometry, history, and future of the universe, and from them the reachability limit of approximately 4.9 billion light-years is derived. This chain of evidence, from Leavitt's Cepheids to Hubble's galaxy measurements to supernova cosmology to CMB precision measurements, spans more than a century of observational astronomy and represents one of the most sustained and successful scientific programs in human history. The reachability limit of 4.9 billion light-years is the product of this entire chain. It is not a number someone computed from first principles. It is a consequence of a vast observational program that has measured the universe with increasing precision over a century. This is worth appreciating. The knowledge that 99.997% of the observable universe is permanently unreachable is not a speculation. It is a conclusion drawn from some of the most precise and well-tested measurements in the history of science. Let us now talk about something that brings the scale of all this back to human experience, about how to hold cosmological knowledge in a way that is neither paralyzing nor falsely optimistic. The reachability limit tells us that most of the universe is permanently inaccessible. This could feel diminishing. Our universe, the part we can ever actually inhabit or affect, is a small fraction of what we can observe. But there is a different way to hold this. Consider what exists within the 0.003%. Billions of galaxies, quintillions of stars, timescales extending to trillions of years. The possibility, uncertain but real, of other civilizations with their own histories and futures within that volume. The reachable portion is not small in any absolute sense. It is only small relative to the full observable universe. In relation to anything humans have ever directly experienced or achieved, it is incomprehensibly vast. We have reached the Moon. We have sent robots to Mars and the outer planets. We have launched one object beyond the solar system at significant speed. We are at the very beginning of any trajectory that might eventually reach other stars or galaxies. The distance from where we are now to the reachability horizon represents a gap of approximately 20 orders of magnitude in distance from the scale of current human achievement to the fundamental physical limit. That gap is not a statement of failure, it is a map of possibility. Everything in between, the inner solar system, the outer solar system, the nearest stars, the Milky Way, the local group, the Virgo supercluster, the billions of galaxies out to 4.9 billion light-years, is, in principle, physically accessible. The physics does not forbid it. What forbids it in practice, or rather what makes it enormously difficult, is our current technological and civilizational situation. We are early. We are at the beginning of a trajectory that, if it continues, might eventually explore a significant portion of the reachable volume. Whether that trajectory continues is not a physics question. It is a question about choices, about what kind of future we build, about whether civilization persists long enough and develops sufficient capability to begin the journey toward the stars. The physics sets a ceiling. What happens below the ceiling depends on us. Let us now talk about the specific stars most likely to be within human reach on the shortest timescales, about the nearest stellar targets that might be plausibly visited within timescales of centuries rather than millennia. Proxima Centauri, 4.24 light-years. A red dwarf star, known to host at least one planet, Proxima Centauri b, in the habitable zone. This is the nearest known star system to the Sun and the most plausible first destination for any interstellar mission. Alpha Centauri A and B, 4.37 light-years. A binary star system of Sun-like stars, possibly hosting planets, though current evidence is uncertain. Part of the same system as Proxima Centauri. Barnard star, 5.96 light-years. A red dwarf with a long history of planet searches. Recent evidence suggests possible planetary companions, though this remains under investigation. Wolf 359, 7.78 light-years. A red dwarf. Lalande 21185, 8.29 light-years. Another red dwarf with possible planetary companions. Sirius, 8.58 light-years. The brightest star in the night sky as seen from Earth. A binary system, very luminous and hot. Not a good candidate for life-bearing planets, but a prominent target. These nearest stellar systems, within 10 light-years, form the immediate neighborhood of our solar system. At 10% of the speed of light, the farthest of these would take less than 90 years to reach. At 20% of the speed of light, the target for proposed laser-driven sail missions, less than 45 years. These are not comfortable timescales by current standards, but they are human timescales, not geological, not astronomical, comparable to a human lifetime or a few generations. This neighborhood, these nearest stars within 10 light-years, represents the realistic near-term frontier of any interstellar expansion, should the technology and will to attempt it ever develop. Beyond this neighborhood, the next 100 light-years, the next 1,000, the next 10,000, the possibilities multiply. More stars, more planetary systems, more potential destinations, all of it within the galaxy, all of it within the local group, all of it well within the reachability horizon. The nearest stars are where the story would begin, if it begins. The reachability horizon at 4.9 billion light-years is where the story ends, if it continues long enough. Between those 2 points lies the entire accessible future of any civilization that might grow from this planet. That is what the night sky contains tonight. The nearest stars, possible first destinations. The Milky Way band, 100 billion stars, 100,000 light-years of possibility. The faint patch of Andromeda, 2.537 million light-years, within the reachable limit, 1 billion years of travel from here at current speeds, but in principle accessible. And beyond, the billions of galaxies of the reachable volume, the permanent horizon of the inaccessible, the darkness full of galaxies we can see but never reach. All of this is real. All of it has been measured. All of it follows from the same physics that governs the atoms in the cells reading these words. Go outside tonight and find a dark place. Let your eyes adjust. Give them a few minutes. Then look up. What you see, the stars, the band of the Milky Way if the sky is dark enough, perhaps the faint smear of Andromeda if you know where to look, is a map, a real physical map of the reachable and the permanently unreachable. The stars you can see with the naked eye are mostly within a few hundred light-years, in principle reachable. Unreachably far by current technology, Voyager 1, the fastest object we have ever launched, would take 73,000 years to reach Proxima Centauri. But physics does not forbid the journey. There is no wall in the way, only distance and time and the technology we have not yet built. The faint patch of Andromeda, barely visible above the constellation of that name in the northern sky, a smear of ancient light requiring dark skies and patience to see, is 2.537 million light-years away. It is the most distant object visible to the naked eye. It is within the reachability limit, in principle accessible. In practice, unreachably far by any current or near-future standard. But within the boundary, on the right side of the line. And beyond what you can see, beyond the reach of the naked eye, visible only through telescopes, are billions of galaxies. Most of them are permanently inaccessible. Not because we lack the technology, because the space between us and them is expanding faster than anything can move through it. Here are the numbers. The observable universe is approximately 93 billion light-years in diameter. We can see this far because light from these regions has had 13.8 billion years to reach us, and the universe has been expanding the whole time. The maximum distance anything originating from Earth could ever physically travel is approximately 4.9 billion light-years. This is not a technological limit. It is a consequence of dark energy, the mysterious component of the universe that is causing the expansion of space to accelerate. Beyond 4.4 billion light-years, space is already receding from us faster than the speed of light. Beyond 4.9 billion light-years, no speed of travel and no amount of time can overcome the expansion. This means that 99.997% of the observable universe is permanently, physically unreachable. Not difficult to reach, unreachable under any circumstances, regardless of technology. This was discovered in 1998 by two independent teams of astronomers studying distant supernovae. They expected to find that the expansion of the universe was slowing down, gravity pulling everything back together. Instead, they found it was speeding up. The discovery earned the 2011 Nobel Prize in Physics. It has since been confirmed by multiple independent methods: the cosmic microwave background, the distribution of galaxies across cosmic time, gravitational lensing surveys. All of them point to the same conclusion. The expansion is accelerating. Dark energy is real. The horizon is real. The limit is real. We happen to live in the accessible 0.003%. This is where we started. This is where the physics of our universe places us. The accessible portion, while small relative to the whole, contains billions of galaxies, quintillions of stars, timescales stretching to trillions of years. The limit constrains the infinite to the merely enormous. We are at the very beginning of any trajectory that might eventually explore this accessible portion. We have reached the Moon, 400,000 kilometers. We have sent robots to Mars, up to 400 million kilometers. We have launched one object, Voyager 1, beyond the solar system, now about 24 billion kilometers out, barely past the threshold. The reachability horizon is 4.9 billion light-years away, roughly 46 quintillion kilometers. Between where we are and where the limit is, that entire space is in principle open. The physics does not forbid it. The stars in the Milky Way, the galaxies of the local group, the billions of galaxies within the reachable volume, all of it, in principle, accessible. What happens between here and there is not a physics question. It is a question about what kind of future civilization builds, about whether it persists, about what it chooses to reach for. The physics sets the ceiling. What happens below the ceiling is still unwritten. Go outside tonight. Find the stars. Find Andromeda if you can. Look slightly above and to the right of the great square of Pegasus in autumn skies. Know that what you are looking at is 2.537 million light years away, that the light reaching your eyes right now left that galaxy before our species existed, that it is within the reachable portion of the universe, on the right side of the limit. Know that most of what exists in the universe is not visible to the naked eye, and most of what is visible through telescopes is permanently, physically beyond the horizon of the accessible. Know that the limit, 4.9 billion light years, was derived not from theory alone, but from measurements, from supernova observations, from the cosmic microwave background,
from the large-scale structure of the universe, from a century of careful astronomical work built on the shoulders of Leavitt and Hubble and hundreds of astronomers who spent their lives measuring what is out there. And know that we are here, on one small planet, in the accessible portion, at the very beginning of whatever comes next. The stars are there. The horizon is there. Everything between here and the horizon, in principle, is reachable.